Good day and welcome to the part 3 of waves at interfaces. Now we'll be building on understanding of the behavior of wave based on the boundary conditions where we obtain the reflection coefficient of amplitude and the transmission coefficient of amplitude. And we'll look at how they can be used to interpret the behavior of the wave. Recall that R subscript 1, 2 circling here is the reflection coefficient of amplitude, and the value ranges between -1 and 1. So the value of the reflection coefficient of amplitude could be -1, minus 0 point anything to 0 to 0 point anything to 1. So the lowest value is -1, the highest value is 1. So when R 1,2, the reflection coefficient is greater than 0, that when it is positive, and that occurs when the wave number in the second medium is lower than that of the first medium. That is, the wave number K1 in the first medium is higher than that of the second medium, K2. Or otherwise you can say the wave number in the second medium, K2, is less than that of the first medium, K1. So when that happens, then it implies that the reflected wave is in phase with the incident wave. Anytime you have a positive reflection coefficient of amplitude, and that means the reflected wave is in phase with the incident wave. That is, the phase angle between the reflected component and the incident component is 0. It's 0. And when you have a negative value of the reflection coefficient of amplitude, that is when K2 is greater than K1, that is when your value lies below 0, minus 0.9, minus 0.8, minus 0.2, minus 0.1, then minus 1. It implies that the reflected wave is not in phase with the incident wave. That is, the reflected wave and the incident wave has wave or the phase difference of 180 degrees. You're not in phase. Okay. The phase difference is greater than 0. The phase difference is greater than 0. That's what it means. Now, for T1,2, which is the transmission coefficient of amplitude between the two medium, 1 and 2 represent the medium 1, medium 2. The value of that transmission coefficient would range between 0 and 2. So, and there's an expression associated with that which relates the transmission coefficient to the reflection coefficient of amplitude, which is T1,2 equals 1 plus R1,2. So from there, if we go back to the reflection coefficient, and when you have 1, when it is positive, put 1. If you put 1 here, put 1 here, where you have R1,2. That means your T1,2 will be 2. And when you have such, that means all the wave is totally transmitted. And the transmitted wave will be in phase with the incident wave. Okay? But when R is negative, -1, then your T1, 2 will be 0. And what does that mean? That means there is no transmission at all. That means the wave will not penetrate the boundary. That means the wave is totally reflected with a phase angle of pi 180 between the incident and the reflected waves. We see that it aligns. So negative this, it shows that the reflected wave is not in phase with the incident wave. Likewise, when you add a negative value and your T is equal to 0, show that the incident and reflected waves are not in phase. You see some consistencies, so very easy to interpret. So any value that is not up to 1 shows that is still reflection takes place, but not absolute reflection. Just like when we have here too. For example, if we have minus half, for example, E minus 0.5 for R12, what does that mean? That means your transmission coefficient will be 1 minus half, which is half. Which will fall within this range. Now that means that part of the wave is transmitted and part is reflected. Okay, so that's understanding. Recall we said that R1, 2, we can use K1 minus K2 over K1 plus K2. Now if the wave number is not known, but we have the linear density of the medium, then you can use this other expression to obtain. And how do we obtain that? And there we know that wave velocity of a wave velocity or wave speed is equal to the angular frequency to the wave number. Likewise, the velocity of a wave in the medium can be obtained from the square root of the ratio of the force of the wave to the density of the medium. And remember we said force remains conserved, but the density of the medium, that density is not it changes depending on the type of media on both sides of the boundary. So you can also use the linear density and also obtain the relationship coefficient of amplitude and that of the transmission coefficient of amplitude. And as the second medium, as the density of that medium increases, then the wave will not be transmitted. Of course, the medium becomes dense. High linear density means a very dense medium. So when the density of a medium increases, a wave will not be able to propagate in such a medium. So what happens in such medium is that there is no transmission. We have total reflection. We have examples. And for example, this example you are given the incident component of the incident wave, then component or the affected component and the transmitted component, and you have to determine the efficient coefficient of amplitude and the transmission coefficient of amplitude. Again, observe that because frequency is constant, no matter the medium or the wave, same wave, then phi, do you see it is constant, omega, angular frequency 555, and k is also the same for the two medium. The incident wave and the reflected wave are in the same medium, so you see k1 we have 33, but it differs in the second medium. So k here, which is k2, is 4. Then you have a1 amplitude of the incident wave, b1 amplitude of the reflected wave, and A2, amplitude of the transmitted wave. So from there you can work it out. So amplitude of the incident wave A1, amplitude of the reflected wave, and the amplitude of the transmitted wave. Then a consistent frequency throughout both media, and the wave number perpendicular to each of the medium. So if you use the formula, you obtain it. So your tension coefficient, a substitute will be 1 minus 1 over 7, and the transmission coefficient will be 6 over 7. Likewise, if you use the formula, T equals 1 plus R, you also obtain the expression. So you could see, so when with minus 1 by 7, that means only a small fraction of the wave is reflected. And negative sign shows that the reflected wave is not in phase with the incident wave. That's what it means. And we'll see bulk of the incident wave is transmitted at 6 over 7. So that means that medium is not dense as such, allowing most of the waves to be transmitted. Then look at this other example. A material serves a barrier to the propagation of a wave, incident direction. So this is the incident. Let me pick a red pink. This is the incident component of the wave. Now, if the direction coefficient is positive and its amplitude is half of that of the incident wave, obtain the expression for the reflected component of the wave. Hence, determine the transmission coefficient of the amplitude for the wave and the expression for the transmitted wave. Now look at it. We have the amplitude of the incident wave, A1. It is 3. Now said, obtain the expression of the. Now it said if the pressure coefficient is positive and its amplitude is half. So it said B1 is positive and B1 is half of A1. Do you get it? So that's where we got this. How we got this? B1 is half of A1. 1.5. Now what will be the expression for the pressure component? Remember, pressure component, your omega is not changing and your K is not changing. But because of direction of X, incident is like this, reflected is like this. So this sign, negative and positive, we have to consider. So if it is positive in the incident wave, it will be negative in the reflected wave. If it's negative here, as we have here, it will be positive in the reflected wave. Okay, but we have omega, we have ky, which is consistent. So what we have is 1.5 cos 2t plus 6s. Now for the second part, which is the transmission coefficient of amplitude for the wave and the expression for the transmitted wave. Likewise, we can also use the expression to obtain know that again R1, 2, which is transmission coefficient, is half. So we can from there get our K, which will be 2. That means K2 is 2. The wave number in the second medium is 2. And we can now obtain our transmission coefficient from this formula, which is 2, 6, K1, then 6 plus 2 is 3 over 2. So transmission coefficient 7.5 also. 7.5. Okay, 0.5. So I now obtain the amplitude for the transmitted wave, which, remember, we said that if E in the first medium is equal to E in the second medium, and in the first medium the E will be the energy of the incident wave, and here we have energy of the reflected wave plus energy of the transmitted wave, and E is related to the amplitude as E is proportional to square of the amplitude. So that's why you have this expression. I'm making the amplitude of the transmitted wave. So here's a formula. You have this expression. Now you solve, you have 2.6. Or you can have it in short form. In short form you have this. And from YT, because incident and transmitted component are in the same direction, so you maintain this negative sign. Then this remains constant. Then you have our K2. You have our A2. You substitute and you have your final expression. It's very straightforward. Okay.